All right, so we've talked about a few different ways of describing distributions. We have talked about measures of central tendency. We've talked about quantiles, which give us key information at different points in the distribution, and the box and whisker plot, which lets us kind of see a summary view of these quantiles and outliers. And most recently, we talked about measures of dispersion, which give us a formal quantification of how much our data points vary in a distribution. So, to wrap up this part of these live lessons, we're going to talk about measures of relatedness, so how we can compare one distribution to another. So if we have two vectors of the same length, x and y, where each element of x is paired with a corresponding element of y, covariance provides a measure of how related these two variables, x and y, are to each other. So when we get into a hands-on code demo, I'll make more sense of what I mean by having values of x and y be paired to each other. So we'll see an example and it'll make more sense. But generally speaking, the idea here is that any element xi needs to be directly related to some element yi. They can't just be a random list of the same length. So for example, this could be the length of a petal, and this could be the width of a petal, or this could be the height of a person, and this could be the weight of a person, but the same person, or the same petal. So these need to be paired in some meaningful way in order for this to mean anything. So, all right. So with all that aside, how do we actually calculate covariance? So similar to how we calculate variance itself, the measure of dispersion, we subtract x bar, our sample mean of x, from each individual instance of x, and we do the same thing for our other variable y. So we subtract y bar, the mean of y, from each instance y. Then, for any given instance, we take the product of these differences and sum up all of those instances. And once we have that sum, we can divide by n, however many samples we have, so however long the vector x is, which must be the same length as our vector y. And that gives us the covariance. So let's jump to a hands-on code demo to see all of this with some real numbers. Okay, so here's our formula of covariance from the whiteboard. Let's use the iris dataset again, which we already used earlier in this notebook, to get some real values to calculate covariance with. So we have 150 measurements of particular iris flowers. So, each row corresponds to a specific iris flower. And so for this first iris in the data set, we know that its sepal length is 5.1, I think, centimeters, and petal length is 1.4 centimeters. So these are definitely paired values. There's a meaningful tie between any instance of one variable. If we call sepal length x and petal length y, then this instance, 5.1, is tied to another specific instance of 1.4. So xi, x0 in this case, is tied specifically to y0 in some meaningful way. So it makes sense to try to see if there is, say, a covariance between sepal length and petal length. Okay, so moving onward with that example, let's literally put sepal length as our vector x and petal length as our vector y. We can use Seaborn to create a scatter plot of x versus y, of the sepal length versus the petal length, and we can see that clearly there is a relationship, that these two variables are related to each other. As petal length gets longer, sepals tend to be longer too. So it seems like there is a relationship, right? It seems like these variables are related. So let's confirm that by calculating the covariance. So n, this is one of the key, so we're now just going to start assembling all the pieces we need for this covariance formula. So n is one of those, which is the length of our sample. So you could use the length of x or of y here. Yeah, I mean, I don't know why I didn't just say x. That seems even easier. And of course, that's going to come out to 150. Both x and y are 150 because there's 150 rows in our iris data set. And then x bar is the mean of our x values. So we sum up all the x values, divide by n. Y bar is the same thing. You could also alternatively use the NumPy mean method, but I kind of just wanted you to see the arithmetic here. And okay, so that gives us some of the values for our formula. So we now have n, we have x bar, we have y bar. Now we can go and iterate over all of the instances in our data set, so each of the rows in this table, and calculate the numerator. So we can calculate xi minus x bar for any given instance I, and similarly calculate yi minus y bar for any given instance, for any given row of this table, and then multiply those two differences by each other. So that is exactly what we're doing right here. So I have an empty list here called product, and then I'm going to iterate over all of the 150 rows in our iris data set, and for each one of those rows, I'll append a new item onto this list that corresponds to xi minus x bar times yi minus y bar. That's exactly what we have in the formula here, right? And then once we have that, we just need to sum up all of the instances and divide by n to get our covariance. So that's what we do here. We sum up all of the individual products, divide by n, and voila, our covariance is equal to 1.266 approximately. So, of course, you don't need to do it in this many steps. I just wanted to show you exactly how this metric works. There is a built-in NumPy cov method for covariance, and this returns what's called a covariance matrix, which in this case here, when we pass in x and y, we get back a 2x2 matrix because x and y together describe a two-dimensional space, right? So you can plot x against y, we have this two-dimensional space, and so we get back a two-dimensional covariance matrix. Before we go on to me explaining what each of these elements are, let's quickly talk about the degrees of freedom again. So we talked about this in a couple of preceding videos, and we've talked about how with any large number of data points, whether we have 0 degrees of freedom or 1 degree of freedom doesn't make a big difference to our results. Again, I'll explain what degrees of freedom are in more detail shortly. It doesn't matter too much right now because I expect that in machine learning we are largely going to be working with large data sets anyway. So for now, just a footnote. And so if you want to get the exact same values as we're getting with these other methods here, as well as with our own calculation of covariance here, then we need to set the degrees of freedom to 0 as opposed to the default of 1. This just again corresponds to whether we have n or n minus 1 in our denominator here. Right, so that was a long footnote. But now we can break down what's in this covariance matrix. So this 1.265, that is here and here. So the covariance is in the bottom left and the top right elements of this matrix. And the other ones along the diagonal, the main diagonal of this 2x2 matrix, those correspond to the variance of x and y respectively. So if we calculate variance using the NumPy variance method that we already discussed earlier in these live lessons, we get the same value as we do in the elements along the main diagonal of the covariance matrix. So that's what all these values represent: variance of x, variance of y, and covariance between x and y. So what this shows, when we have a positive covariance, that means that there's a positive relationship between the two variables. So what that means is that as our sepal length gets larger, that corresponds to a larger petal length. So there's a positive covariance. If x and y are inversely related, then the opposite is true. Their covariance is negative. So if as sepal length got larger, petal length got smaller, that would be a negative relationship, an inverse relationship, and we would have a negative covariance. And also, the less related two variables are, the closer that their covariance is to 0. So for example, somewhat to my surprise, sepal length and sepal width are not really related to each other. And we can see that in this chart here. So whereas we can see in this chart there's a clear relationship between sepal length and petal length, I might have thought that long sepals would also be wider sepals. And if you want to get rid of this error here, it's a quick fix. It's actually not an error, it's just a warning. So not critical. We can fix it up like that. So making our arguments explicit as opposed to positional fixes that warning. And yeah, so interestingly, I'd expect sepal length to correspond to sepal width, but there isn't really a strong relationship like there was between petal length and sepal length. So when we calculate the covariance of these two variables, correspondingly we have a much smaller covariance. The covariance is quite close to 0. There's this extremely minor negative relationship that probably isn't really meaningful. It isn't what we'd call statistically significant, a topic that we'll talk about later on in these live lessons. We're not quite ready for statistical significance discussions yet, but this looks like it's so close to 0 that it probably means there's no meaningful relationship between these two variables. All right, so that covers covariance, our first measure of relatedness. Up next, I'm going to talk about correlation, which is a derivation of covariance, but is much more common. We'll see why in the next video.